Welcome to the second presentation in Unit 8. It's entitled Fender Stratocaster. It says famous people that feel that they must perpetually be on the crest of a wave, not realizing that it is against all the rules of life. You can't be on top all the time. It isn't natural. So you're going to have to hit a crest at some point. Okay, so the learning goals for this particular presentation are that you'll be able to use the inverse relationship between period and frequency, that you'll be able to identify the factors that affect the velocity of a wave, and that you'll be able to use the wave equation to determine an unknown. So, what we already know that there are two major classifications of waves, transverse and longitudinal. What you see here pictured is a transverse wave, but you can also have a longitudinal wave where you have stretched out, compressed, stretched out, compressed, and that would be an example of a longitudinal wave. You know that waves are generally defined by their wavelength, their period, their frequency, and their amplitude, not to mention their crests and their troughs and all kinds of other factors. But what we learned in the lab was there's a direct relationship between frequency and harmonic number. The frequency has no impact on velocity. So no matter how fast you made that little motor drive that wave, it didn't affect the velocity of the wave on the string. In fact, the only thing that mattered as far as the velocity on the wave, the velocity of the wave on the string, is the medium in which it travels. If you were to take the string and pull it tighter, you'd get a different velocity. If you were to take the string and make it looser, you'd get a different velocity. If you were to use a different string, you'd get a different velocity. It's the medium in which the wave travels that determines how fast it goes. Okay, so frequency. The first thing we need to talk about is frequency. We've already defined frequency as the number of cycles per second, and we've already defined period as the time it takes to complete a cycle. But what you should know is that they're inversely related. If you think of frequency as number of cycles per second. Okay, that's a great definition for frequency. How many waves are there? Now if you were to look at period, period is the number of seconds per cycle. So if you look, they're just inverses of one another. If you were to somehow flip this over, you would get this. So that's what we have here. It's the relationship between frequency and period. Frequency and period is F equals 1 over T, where T is in seconds. Now, frequency is generally measured in hertz, which is capital H lowercase z. But a hertz is the same thing as a 1 over second. That's what it means to be 1 hertz equals 1 over seconds. So it's just the inverse of seconds, and it gets its own special name because it's a hertz. Okay? So if we were looking at this, which describes the relationship between frequency and period? If you were to look at it, the equation that we have is F equals 1 over T. So I'm going to make T my X value. So I were to put T here. As I increase the value of T, what you should see is that there's a decrease in the frequency. So that's not a direct relationship. A direct relationship is they go up together. It's not a quadratic relationship because that would say as this goes up, this gets way bigger. And that's not the case. So you have to decide if it's an inverse or an inverse square. If you look, there's nothing squared here, so the best answer is it's an inverse relationship. Next it says your favorite radio station is 820 kilohertz. Let's determine the period of this wave. So whenever you look at the AM or at the dial, AM actually means kilohertz. So because of that, whenever you're saying I want to listen to 820 AM, you're saying I want to listen to 820 kilohertz. So we want to determine the period of this particular wave. In order to do that, let's first identify what this is. This is a frequency. So I would say frequency is equal to 820 kilohertz. Now you should recognize that frequency is supposed to be in hertz. So just like you would convert kilometers to meters or kilograms to grams, you're going to have to convert kilohertz into hertz. So you would say 1 kilohertz is equal to 1,000 hertz, or you get a frequency of 820,000 hertz. Okay, now I want to solve for the time, and I would use the equation 1, F equals 1 over T. When you do this, you get 820,000 equals 1 over T. Now at this point, a lot of people will have some issues with the math. Okay, whenever you're doing the math, you realize people just say, well, it's automatically the same. It's not, because remember, 1 over T is this. 1 over 2 is not the same thing as 2 over 1. They're different values. 1 over t is not the same thing as t over 1. So you need to multiply both sides by t, and when you do that, you now have 820,000 t equals 1. Now you can divide both sides by 820,000, and you can put into your calculator what 1 over 820,000 is, and when you do, you should get something like the period is 1.22 times 10 to the minus 6th seconds. The third question we have says, what is the frequency of a wave that completes 5 cycles in 15 seconds? Now remember, the definition of frequency is cycles per second. So if I have the number of cycles, it goes on top. If I have the number of seconds, it goes on bottom. So the very definition would mean it's 0.33 hertz. Okay, so we also introduced the idea of the velocity equation, or excuse me, the velocity wave equation, which is v equals lambda f. It's how you calculate the velocity of a wave. So we have a couple of new variables here. We have talked about frequency, and frequency is f, and it's measured in hertz, and all those sorts of things. You should be very, very familiar with velocity by now. Velocity is measured in meters per second and all those things. This is a new one right here. It's actually a Greek letter lambda. And the Greek letter lambda, we'll write it out. Greek letter lambda actually stands for the wavelength. The wavelength is, remember, the distance between subsequent points on a wave. So here to here, what is that distance? So the wavelength is a length. So we're going to measure it in meters just like we do with distance and displacement and all those other units of distance. So we're going to measure it in meters, and it can be measured with a meter stick. So now you have this idea of v equals lambda f. Remember before when we talked about the idea that frequency, although it's measured in hertz, 1 hertz is really just 1 over seconds. Well, if we were to look at it now, wavelength is measured in meters, frequency is measured in 1 over seconds, so when you multiply those together, you get meters over seconds, which is the unit for velocity. So that's why we have to have it in meters and meters per second in hertz. So we have an equation here. It says astronomy examines the universe by looking at different frequencies. Gamma astronomy uses frequencies larger than 1 times 10 to the 19th hertz. So this is a really big number. Radio astronomy looks at waves smaller than 3 times 10 to the 11th hertz. Match the telescope used to capture the radiation with the appropriate frequency. So the first thing that you should realize is this is something called a very large array. It not only consists of multiple huge satellite dishes, they're actually spread out in a pattern that almost make them their own larger satellite. Okay, so this is an extremely large area. This is a satellite. Satellites, by definition, have to be relatively small because they have to be small enough for us to put them in orbit. So what I have is I have something very, very small, and I have something very, very large. Now I want to know which one's going to be useful for me in terms of which radiation. Now, a lot of times people will just go, oh, big, 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 small, or small, small. So you would go that way, but that's not the case. In this case, you're given the frequencies. These right here are values of frequencies because they're measured in hertz. So this is right here is a frequency because it's measured in hertz. These are about physical size, and these are wavelengths. If you were to look at the equation, you have the equation v equals lambda f. Now you may not know this quite yet, but all radiation, gamma radiation, infrared radiation, visible light, radio waves, they all travel at the same speed. So this is a constant. So I'm going to cancel this out. I'm going to put c for constant right now. If I put c for constant, that means as this number goes up, this number goes down. So the one with the lowest frequency, and the lowest frequency that we have is here, has to be the one that's the largest in size and therefore would need the largest telescope array. This is called the Very Large Array, and it's used as a radio telescope. This right here is a gamma ray telescope that is actually situated in space, and the reason why it's in space is because gamma rays generally don't penetrate the atmosphere, which is a good thing because it would be bad if they did. Next, we have proficient. It says determine the velocity of an ocean wave if it has a frequency of 3 hertz and a wavelength of 5 meters. So I'm trying to solve for the velocity. Question mark. It's a bad question mark. We have frequency equals 3 hertz. We have the wavelength equals 5 meters. And I want to use the equation v equals lambda f. When I do that, all the units check out the way they're supposed to, so I can say v equals 5 times 3, or 15 meters per second. The next one says if this wave has a frequency of 200 FM, and it says FM is 1 megahertz, then what is the velocity of this wave? So here's where you got to be kind of tricky. It says that this length right here is 3 meters, and people write down wavelength is 3 meters. And if you do that, that's wrong. If you go back to the diagram, remember the wavelength is the distance for subsequent parts or successive parts of the wave. Here I'm at a trough, here I'm at a trough. So this actually constitutes one wave. If I go from here to here to here, that actually represents two waves. So one wavelength would actually be 1.5 meters. Next, you have the frequency. The frequency is 200 FM, but you should realize that FM is not a standard unit that you're going to work in. So it actually says FM means 1 megahertz. So you would say 200 megahertz. Well, megahertz isn't what you're supposed to work in either. So you would say 1 megahertz and you would do your conversion. You could look it up and you could say 1 megahertz is a million hertz. And when you do that, you end up with a value of about 2 times 10 to the 8th hertz. That right there represents a very, very high frequency, which makes sense for this particular wave. So now we plug in the equation. I'm still trying to solve for velocity. Whenever I plug in the equation v equals lambda f, I have 1.5 times 2 times 10 to the 8th. Whenever I multiply those out, I get 3 times 10 to the 8th. This right here is a very special number, this 3 times 10 to the 8th. What that number represents, it represents the speed of light. And it's actually going to come up quite a bit when we talk about Unit 9, whenever we're talking about electromagnetic waves. Any wave that travels at this 3 times 10 to the 8th is considered to be part of what we call the electromagnetic spectrum. So it's radio waves, microwaves, infrared waves, visible light, UV, X, and gamma rays. Okay, so those are all the parts of the electromagnetic spectrum because they all travel at that. Next we have earthquakes. We're going to learn a little bit more about earthquakes. Earthquakes have two waves, and we kind of talked about that a little bit in the first one. The first one is the longitudinal P wave, and the longitudinal P wave actually travels the fastest. It doesn't cause major damage. It just it goes through the earth, and we can detect it, and it's the fastest one. Now the S wave, which is sometimes called the shear wave, it travels at about 60% of the P wave, and it is the source of the major damage. Now the good news is that it travels at 8 kilometers per second, and this one is much slower. So for example, if this one travels at 8 kilometers per second, and once again it depends on what it's traveling through, whether it's rock or sediment or those sorts of things, this would travel at about 4.8 kilometers per second. The disparity in speeds that you have here actually give you a chance to have some sort of warning system. Okay, it's not a very fast system, it's not a very long system. It's not going to say like, hey, there's going to be an earthquake in 20 minutes. It's more of a, hey, you have 5 seconds before the earthquake gets to you. So it gives you just enough chance for you to get cover based on the fact that these two waves travel at different speeds. Now, mastery. This is a tough question. Okay, what it says the epicenter of an earthquake is 20 kilometers away. How long do you have after the P wave arrives to prepare for the S wave, assuming the P wave travels at 5 kilometers per second? So what I have is I have the total distance that's going to be traveled by the waves, and I'm going to go ahead and convert it. To meters, just because we should be working in meters. I also have the velocity of the P wave. The velocity of the P wave is going to be 5,000 meters per second. I also have the velocity of the S wave, because remember the S wave travels at 60% of the P wave. So I can say the velocity of the shear wave is at 3,000 meters per second, which is what I get when I take 5,000 and I multiply it by 60%. So now I have these things right here, and I want to figure out what the time it takes, the time difference that I have. And so what I'm going to do is I'm going to do the equation d equals v over t, or excuse me, d equals v times t, which is just a rearrangement of the very first equation that we learned in this class. Velocity equals distance over time. So what I'm going to do is I'm going to do it for both waves, and I'm going to do them in different colors. So I'm going to say 20,000 equals 5,000 t. And I'm going to solve by dividing both sides by 5,000. And when I do that, I get t equals 4. So it takes about 4 seconds for the P wave to arrive. Now I'm going to change colors because I'm switching waves. We're going to say the shear wave. I'm going to do 20,000 equals 3,000 T. Now 3,000 T, divide both sides by 3,000, and you get T is equal to 6.67 seconds. Now the question says, how long do you have to prepare after the P wave arrives? So it takes 4 seconds for the first wave to get there. It takes 6.67 seconds for the second one to get there. So you have about 2.67 seconds. Now that doesn't seem like it's a lot of time, but it's enough time for you to get into under a doorway or get into a duck and cover position or something along those lines to protect your head or to brace yourself so things don't fall on you. Any amount of time would help. Okay, so the last thing we have to talk about in this particular presentation is the velocity of a wave. Now remember, the velocity of the wave depends only on the medium in which it travels. It does not depend on how much energy you put into it. Remember, if you put a lot of energy into it, what happens is it starts to have a big amplitude as opposed to a small amplitude. So energy is related to the amplitude, not to the velocity. And that's a little bit different than what we talk about when we talk about traditional mechanics. Before, if you put more energy into a car, the car will go faster. That's not the case when we're talking about waves. The wave's velocity depends solely on what it's traveling in. So, waves on a string. The velocity, the thicker the mass, or excuse me, the thicker the string, the higher the mass, the slower the wave, the harder it is to displace. You can actually see this whenever you have a guitar. The guitar consists of multiple strings depending on what type of guitar you have. The last string right here is the largest and thickest string, and it produces the lowest sound. The reason why it produces the lowest sound is because the waves actually travel the slowest on that one, producing a lower frequency. These right here are the thinnest strings. The thinnest strings have the highest velocity and therefore produce the highest sounds. You can also adjust what the guitar sounds like by, you can turn these knobs at the top. Whenever you turn the knobs at the top, what it actually does is it pulls these strings tighter or makes them looser. By changing the tension in the string, that's how tight it is, by changing that tension in the string, you're actually changing how fast the wave travels again, and therefore changing what it sounds like. This is an equation that you can actually use to calculate that. The velocity of a string, the velocity of a wave on a string depends on these two things. The square root of Ft, where Ft is what we call the tension. Remember, anytime you have an F, it's a force. This T just describes the force. Excuse me, this mu term represents what we call the linear density. The linear density is just basically a ratio of what's the mass divided by how long is the string, divided by the length of the string. So the mass has to be in kilograms, and that's kind of tough whenever we're talking about things like a guitar string, because guitar strings, they're not going to be measured in a kilogram ratio, but they need to be in this particular case. So generally speaking, the linear density is a small number, like 0.001, something along those lines, as opposed to something like 10. It's not going to be that high. So this allows you to calculate the velocity of a wave on a string, and our last couple of examples that we have are going to deal with that. The first one says proficient D1. It says, what is the linear density? So I'm actually trying to solve for the mu value. That's the Greek letter mu. What is the linear density of a string that generates a 35 meter per second wave when subjected to 150 newtons of force? So the first thing you realize is you assign everything to variables. You have Ft is 150 newtons. You have the velocity is 35. And everything's in the units that it's supposed to be in. Okay, since it's supposed to be in these particular units, we'd plug it into the equation. Velocity equals Ft divided by mu square root. So now we would say 35 equals the square root of 150 divided by mu. Okay, at this point, you would need to plug it into or you would square both sides. Okay, whenever you square both sides, you're going to have some number, or actually you're going to have 150 over mu equals some number. Okay, at this point you need to do algebra, and you should by now be able to switch this number and this mu value using algebra, and you should get mu is equal to 0.122 kilograms per meter. The last example says a guitar wants to play middle C. at 523.251 hertz. The guitar is constructed with a 1 meter piece of string with a mass of 0.005 kilograms. What tension must the string have to produce the note indicated? Okay, so this is a tough one right here. It involves one piece of information that you may not be quite familiar with, and that's going to be this. Actually, you should be familiar with it from the lab. Whenever you have this, a standing wave, that represents one wavelength. Whenever you have a guitar, it looks like this. It's like the first harmonic. The first harmonic means that this thing has half of one wavelength. So this is half of a wavelength. So because of this, I know it's a 1 meter string that's producing half of a wavelength. I can say that the wavelength is 2 meters. I know that the frequency is 523.51 hertz. I know that the mass is 0.005. I know that the length of the string is going to be 1, which means when I take those two and I divide them out, I get my mu value, which is 0.005. So now that I have these known variables, I can realize that I actually have two equations for V. I have V equals lambda F, and on the other side I can say V equals Ft over mu. Well, what you can do is you can actually set these two equal to each other. And in this particular case, you can say the square root of Ft over 0.005 equals 2 times 523.51. If you take these, the first thing you would have to do is you'd have to square both sides. Whenever you square both sides, you have to square everything on the right. So you end up with something like Ft over 0.005 equals a pretty large number at this point. Then you would multiply it by 0.005, and when you do that, you should get a tension of around 5,480 newtons, which is pretty ridiculous. Now, the reason why it's so ridiculous is because our numbers as far as the the linear density of the string is pretty far off. But that's what we get for this particular example.